Welcome. I'm so glad you found your way here to this quiet space. Tonight, we are going to explore a story that is as old as the world itself. The story of water. It is a gentle, eternal rhythm, a cycle that never truly begins and never truly ends. As you settle into your blankets and find a position that feels just right, let the sound of my voice be a soft guide, leading you away from the noise of the day and into a state of calm, curious rest. Think for a moment about the sheer scale of our blue planet. There are approximately 326 million cubic miles of water on Earth. It is a number so vast it feels more like a poem than a measurement. Every ocean, every hidden underground aquifer, every drifting cloud, and every dewdrop on a morning leaf is part of this singular, massive treasury. Our first realization tonight is that Earth is essentially a closed system. This means that the amount of water we have today is the same amount we have had for billions of years. We do not receive new shipments of water from the stars, and very little of it ever escapes our atmosphere into the void of space. It stays here, cradled by gravity, changing its shape, but never its essence. The origins of this water are as mysterious as they are ancient. Many scientists believe that much of our water arrived here during the chaotic infancy of the solar system, carried by icy comets and asteroids that tumbled through the darkness to find a home on a young, cooling Earth. Others suggest it was locked deep within the planet's primary rocks, released slowly as steam through the breath of early volcanoes. Because of this, the water you encounter every day is unimaginably old. The molecules in a summer rainstorm or the steam rising from a cup of tea are nearly 4.6 billion years old. They were present when the Earth was nothing more than a glowing ember, and they have remained here through every age of ice and every era of heat. If you find that these quiet reflections help you drift toward a peaceful sleep, you might consider subscribing to the channel or leaving a gentle like on this video. It is a small way to help this quiet corner of the internet grow, ensuring that others can also find a place of rest. But for now, there is nothing you need to do. Just listen and let your breath slow down. Over 70% of our world's surface is covered by this ancient substance. It is the lifeblood of the planet, a blue veil that regulates our temperature and sustains every living cell. When you look at a map of the world, you are looking at a map of water's journey. It is a profound thought to hold as you close your eyes. Every drop of water has been here since the beginning. It has been frozen in prehistoric glaciers, flowed through the hearts of ancient forests, and rested in the deepest trenches of the sea. It is a traveler of time, a constant companion to the Earth. But to truly understand this vast global rhythm, we must look closer. We must leave the scale of oceans and continents behind and move into the microscopic world. Imagine yourself shrinking down, smaller than a grain of sand, smaller than a speck of dust, until you are standing face to face with a single, tiny molecule of H2O. This is where the magic of the cycle truly begins, in the invisible architecture of a single drop. Imagine you are drifting closer to that single molecule, leaving the vastness of the ocean behind to look at the very foundation of life. It is a tiny, elegant structure composed of just 3 parts, one relatively large oxygen atom and 2 stellar hydrogen atoms. Together, they form a shape that resembles a wide, gentle V, or perhaps the silhouette of a quiet, resting bird with its wings slightly spread. This specific V-show shape is not accidental. The two hydrogen atoms sit at one end of the oxygen atom, creating an angle of about 104.5 degrees. This humble geometric arrangement is one of the most important secrets in all of nature. Because of the way these atoms share their energy, the molecule becomes what scientists call polar. The oxygen side carries a very faint negative charge, while the hydrogen side carries a faint positive charge. You can think of each water molecule as a tiny microscopic magnet. This creates a beautiful, invisible quality known as stickiness. Because opposites attract, the positive hydrogen arms of one molecule are naturally drawn to the negative oxygen body of another. They don't fuse together permanently. Instead, they perform a constant graceful dance, reaching out to hold hands for a brief moment before letting go and finding a new partner. This gentle, persistent tug is called a hydrogen bond. It is fascinating to realize that the massive structures of our world, the towering clouds that catch the sunset, the rhythmic tides of the Atlantic, and the soft blankets of winter snow, all find their origin in this one tiny bent shape. If the H2O molecule were straight instead of a V, or if it didn't have this magnetic stickiness, water would not behave the way we know it. It would likely remain a gas at the temperatures we find on Earth, drifting away into the atmosphere. There would be no oceans to cradle the continents, no rain to nourish the soil, and no life to witness the turning of the seasons. This molecular stickiness or cohesion is what allows water to clump together into perfect, shimmering spheres of dew on a morning leaf. It is what gives water its surface tension, creating a delicate skin that allows small insects to glide across a pond as if they were walking on glass. Every time you see a raindrop clinging to a window pane, you are seeing the strength of billions of these tiny V shapes refusing to let go of one another. As we watch these molecules interact, we begin to see how their behavior changes based on how much energy is flowing through them. This invisible architecture is the reason water can transform so completely, shifting its identity while keeping its essence. It is a journey of movement and stillness, a transition between different states of being that allows the water cycle to breathe. We are about to move from the quiet dance of the molecule into the three distinct worlds that water inhabits on our planet: the solid, the liquid, and the gas. There is something deeply comforting about the way water changes its form, moving between states of being with a quiet, predictable grace. On our planet, water is a shapeshifter, existing as a solid, a liquid, and an invisible gas. It is a rare and beautiful thing to realize that Earth is one of the few places in the known universe where all three of these states occur naturally at the same time. This is because our world sits at just the right distance from our star, in a region often called the Goldilocks zone, where the temperature is neither too harsh nor too mild, allowing water to cycle through its various lives. When we think of things getting colder, we often imagine them shrinking, pulling inward to stay warm. Most substances in nature follow this rule. As they lose heat, their molecules slow down and pack more tightly together, becoming heavier and denser. But water possesses a quiet, rebellious nature. When liquid water cools toward the freezing point, it begins to behave in a way that seems almost magical. Instead of huddling closer, the molecules begin to push each other away. Those V-shaped structures we spoke of earlier start to align themselves into a very specific, orderly pattern. They form a delicate hexagonal lattice, a microscopic honeycomb of ice. Because of this unique crystal structure, ice actually contains more empty space than liquid water does. This means that when water freezes, it expands, taking up more room than it did before. This expansion is why ice is less dense than the liquid it came from, and it is the reason for one of the most important sights in the natural world, ice floats. If ice were like most other substances, it would sink to the bottom of our lakes and oceans as it froze. Over time, the depths of the world would fill with permanent, sunless ice, and the life within them would have nowhere to go. But because ice rises to the surface, it creates a floating crystalline ceiling. This layer of ice acts as a brilliant insulator, a frozen blanket that traps the relative warmth of the water below and shields it from the biting air above. Beneath this quiet white shield, the water remains liquid, and the life within it, the sleeping fish, the dormant plants, and the tiny organisms, can survive through the long, dark months of winter. As you listen to the story of this protective layer, take a moment to notice your own surroundings. Adjust your pillow if you need to, finding that perfect spot where your neck and shoulders can fully release. Feel the gentle weight of your body sinking into the mattress, supported and safe, much like the life resting beneath the winter ice. Allow your breath to be slow and easy, matching the unhurried pace of the seasons. It is a profound comfort to know that the very physics of a water molecule are designed to protect the world. This balance between solid, liquid, gas is the heartbeat of our planet's climate. Without this constant shifting of states, the Earth would be a very different, much lonelier place. We live in a world where the same substance can be a hard glacier, a flowing river, and a soft, invisible vapor all at once. But this movement, this constant changing from one state to another, requires a guide. It needs a source of power to stir the molecules and give them the strength to rise. To understand how the cycle begins its upward journey, we must look away from the frozen lakes and toward the distant, golden engine that drives everything we see. We must turn our attention to the sun, whose warmth reaches across the vastness of space to touch the surface of our world. The sun is our planet's silent, golden engine. Even though it sits nearly 93 million miles away, its presence is felt in every ripple of a lake and every wave that breaks upon the shore. This distance is almost impossible to imagine, yet the energy the sun releases travels across that vast, dark void with incredible purpose. It moves in the form of solar radiation, gentle waves of light that take only about 8 minutes and 20 seconds to reach us. By the time that light touches your skin on a warm afternoon or glints off the surface of the sea, it has completed a journey of nearly 100 million miles, arriving with just enough strength to set the world in motion. When these beams of light strike the vast blue expanse of the ocean, something beautiful happens. The water doesn't simply reflect the light like a mirror, it breathes it in. The ocean is a massive reservoir of energy, and its surface acts as a gateway. As the sunlight enters the water, it begins to transform. The energy of the light is absorbed by the water molecules, turning from pure radiance into a soft, deep warmth. Most of this heating happens in the very top layer of the sea, the upper 100 meters, where the sun's influence is strongest and most life-giving. Interestingly, not all light travels through the water in the same way. You might wonder why the deep ocean looks the way it does. The reds and yellows of the light spectrum are absorbed quickly near the surface, their energy being used to warm the topmost layers. However, the cool, calm blue light has a shorter wavelength, allowing it to travel much deeper into the column of water. This is why, as you look down into the clear depths of a tropical sea, the world turns a rich, peaceful indigo. The water is filtering the sun's energy, holding on to the warmth while letting the blue light wander through the shadows. This relationship between the sun and our water is perfectly balanced. If the earth were just a little bit closer to the sun, the heat would be too intense, and our oceans would eventually boil away into a thick, suffocating mist. If we were just a little further away, the world would lock itself in a permanent, icy slumber. But the Earth sits in what is often called the Goldilocks zone, the perfect distance where the sun provides exactly the right amount of energy. It is enough to stir the water and keep it fluid and moving, without ever overwhelming the delicate systems that keep our planet habitable. As you rest, imagine this massive, rhythmic exchange of energy happening across half the world at any given moment. The sun is not just a light in the sky. It is the hand that reaches down to pull the water upward. This gentle warming is the catalyst for everything that follows. As the sun's rays continue to pour down onto the tropical seas and the quiet lagoons, the water molecules at the very surface begin to react. They are no longer content to sit still. They start to vibrate with a new kind of energy, gathering the strength they need to make a monumental change. This is the beginning of a silent, invisible exodus, the moment where the liquid world prepares to leave the ground and join the sky. Imagine a vast, calm ocean under the afternoon sun. While everything looks still from a distance, a silent, miraculous transformation is taking place at the very edge of the water. This is the invisible transition of liquid water into the air, a process that requires no sound and no effort from us. Yet, it is one of the most powerful movements on our planet. It is an invisible bridge being built between the sea and the sky, molecule by molecule. As you settle deeper into your rest, try to visualize this quiet boundary where the water meets the atmosphere. It is a thin, shimmering veil. This movement all begins with something called kinetic energy. Think of the water molecules as tiny, restless dancers. As the sun warms them, they begin to vibrate and move with increasing speed. The warmer the water becomes, the more energetic these dancers get, bouncing off one another in a frantic, microscopic ballet. Each molecule is like a tiny magnet, clinging to its neighbors with a soft but firm grip, held together by the stickiness of their hydrogen bonds. To leave the ocean and join the air, a molecule must gain enough energy to overcome this grip. It needs a boost, a push from the sun's rays. When that energy arrives, the molecule begins to spin and jiggle faster and faster until it reaches a critical speed. This is the moment of liberation. It is moving with such intensity that its neighbors can no longer hold it back. Like a bird taking flight, a single molecule of H2O snaps away from the surface and leaps into the air above. There is a beautiful hidden logic to this process. Because it is only the fastest, most energetic molecules that manage to escape, the water left behind actually loses a little bit of its total energy. This is why evaporation is known as a cooling process. It is the same reason a gentle breeze feels cool against your skin on a summer day. The water is taking a bit of heat away with it as it departs. Once the molecule enters the air, it changes its identity entirely. It is no longer a liquid, it has become water vapor. We often think of clouds or steam as vapor, but true water vapor is completely invisible. It is a clear, transparent gas, mixing silently with the nitrogen and oxygen of our atmosphere, hiding in plain sight. The scale of this invisible event is truly staggering. In every square inch of the ocean surface, millions of molecules are leaping into the air every single second. Across the entire globe, this adds up to an almost unfathomable amount of water rising toward the stars. If our eyes could see this invisible mist, the sky would look like a shimmering, upward-flowing river, a silent golden glow rising from the waves. It is a constant, gentle exodus, lifting the weight of the sea into the lightness of the air. It is the Earth's way of breathing, taking the heavy and making it light, taking the salt-laden and making it pure. As we watch this invisible rise in our mind's eye, we begin to realize that the ocean is the great heart of this system. However, it is not the only source of the moisture that fills our air. The land beneath us, though it may seem solid and still, is also part of this breathing rhythm. Even as the sea exhales its invisible mist, the vast green reaches of the world are preparing their own contribution to the clouds above. The water cycle is a grand partnership between the deep blue of the waves and the vibrant, living green of the earth. Imagine standing at the edge of a deep green forest as the sun begins to warm the morning air. There is a profound stillness here, yet beneath that silence, a massive, living engine is at work. This is the breath of the forest and the fields, a process just as vital as the evaporation from the sea, but one that is driven by the quiet pulse of life itself. While the ocean provides the vast majority of the world's moisture, nearly 10% of the water in our atmosphere comes from the land, released through a gentle phenomenon known as transpiration. If you were to look closely at the underside of a single leaf, perhaps the leaf of a soft maple or a sturdy oak, you would find thousands of microscopic openings called stomata. These are the tiny mouths of the plant world. Their primary job is to take in the carbon dioxide the plant needs to grow. But as they open to breathe, they inevitably allow a little bit of moisture to escape. This isn't a mistake of nature. It is a beautiful, cooling exhale. This release of water vapor acts as a natural air conditioner for the plant, keeping its tissues cool under the heat of the sun. much like the way a gentle mist might cool your skin. The scale of this biological exhale is truly remarkable. A single large oak tree can release as much as 40,000 gallons of water into the air in a single year. If you imagine a vast field of corn, every acre of those green stalks is lifting nearly 4,000 gallons of water into the sky every single day. It is a constant, rhythmic contribution to the clouds, a gift from the roots of the earth to the heights of the heavens. There is a quiet wonder in how this water moves. Think of a giant redwood tree standing over 300 feet tall in the misty forests of the coast. To reach the very highest needles, a drop of water must travel a distance equivalent to a 30-story building, moving directly against the relentless pull of gravity. It does this without a heart to pump it or a motor to drive it. Instead, it relies on that same stickiness of the water molecule we spoke of earlier. As one molecule evaporates from a leaf at the very top, it pulls on the molecule behind it, which pulls on the next, creating an unbroken chain of water, stretching all the way down to the roots buried deep in the cool soil. It is a silent, liquid rope being pulled upward by the sun. In places like the Amazon rainforest, this process is so powerful that it creates what scientists call fleeing rivers. These are massive corridors of water vapor that move through the air, carrying more water than the Amazon River itself carries on the ground. These invisible rivers in the sky dictate the weather for entire continents, proving that the forest is not just a passenger of the water cycle, but an active creator of it. As we leave the warmth of the humid forests and the sun-drenched fields, we find that the water cycle does not stop where the greenery ends. Even in the coldest, most desolate corners of our world, where the ground is locked in ice and the air is biting and crisp, the journey continues. In the high, silent reaches of the mountains, water finds yet another way to take flight, transforming in a way that seems almost like magic, moving from the solid grip of the frost directly into the freedom of the air. Imagine yourself standing on a high granite ridge where the air is thin and so crisp it feels like it might crack. All around you, the world is draped in a heavy blanket of white. It is so cold here that the thought of a running stream or a melting puddle feels impossible, a memory from a different season. And yet, if you were to stay here for days, watching a single snowdrift under the bright, high-altitude sun, you would notice something strange. The snow is shrinking. It isn't melting into the soil, and there are no damp patches on the rocks beneath it. The snow is simply vanishing, turning directly from a solid crystal into a ghost of vapor. This quiet transformation is called sublimation. It is one of the most poetic parts of the water cycle, where ice and snow choose to skip the liquid phase entirely. Instead of the slow, messy transition into a puddle, the water molecules receive just enough energy from the sun to break free from their frozen structure and leap straight into the sky. It is a graceful, invisible exodus that happens in the coldest reaches of our planet, from the peaks of the Himalayas to the vast frozen deserts of Antarctica. For sublimation to occur, the conditions must be just right. The air needs to be very dry with low humidity, and the sun must be bright enough to vibrate the molecules at the surface of the ice. Often, a dry wind helps the process along, whisking away the newly formed vapor before it has a chance to settle back down. In some of the world's great mountain ranges, like the Andes or the Rocky Mountains, as much as half of the winter snowfall can return to the atmosphere through sublimation before the spring thaw even begins. It is a reminder that the water cycle is always in motion, even when the world seems locked in a deep frozen sleep. You can see this same process in your own home, in the quiet darkness of your freezer. If you have ever left an ice cube tray for too long, you might have noticed that the cubes have grown smaller, pulling away from the edges of their plastic molds. Or perhaps you've seen freezer burn on a package of food. Those tiny white frost crystals are actually water that has sublimated out of the food and then refrozen nearby. Even in the stillness of a machine, the ancient laws of the water cycle are at work, moving molecules from one state to another. On a much grander scale, sublimation is what allows the polar ice caps of Mars to grow and shrink with the seasons. Because the Martian atmosphere is so thin and cold, liquid water cannot easily exist on the surface. Instead, the vast fields of ice turn directly into gas, creating thin, wispy clouds in a distant sky. Whether on another planet or on a mountaintop right here on Earth, this process proves that the journey of water is relentless. Cold is not a barrier. It is simply another path for the cycle to take. As we stand on this mountain peak, we realize that the air around us is much more than empty space. It is a vast, invisible reservoir, currently holding all the moisture that has risen from the oceans, the forests, and these frozen slopes. This vapor is now a part of the atmosphere, a layer of gases that wraps around the Earth like a soft, protective shell. To understand how this moisture will eventually find its way back down to us, we must look closer at the air itself, not just as a collection of gases, but as a physical environment with its own unique tensions and limits. The water vapor is now a guest in this aerial world, waiting for the right moment to gather its strength and transform once again. As we watch these invisible molecules drift through the air, we might wonder how they ever find their way back to one another to form the clouds and rain we know so well. Water has a remarkable quality that we often take for granted. It is incredibly sticky. On a molecular level, water molecules are drawn to each other with a force called cohesion. This internal attraction creates what scientists call surface tension, a kind of invisible skin that pulls the liquid inward. It is one of nature's most subtle yet powerful forces. In fact, among all common liquids that aren't liquid metals, water has the highest surface tension of them all. Imagine a tiny water strider, its delicate legs resting on the surface of a quiet garden pond. It doesn't sink. Instead, the water's surface bows slightly under its weight, like a trampoline made of liquid. This is surface tension in action, a testament to how tightly those H2O molecules are holding on to one another. This same tension is what forces water to form into droplets. Whether it's a bead of morning dew on a blade of grass, or a tiny stick of moisture suspended in a high-altitude cloud, the water is constantly trying to pull itself into the most compact shape possible. A sphere. A sphere has the smallest surface area for its volume, making it the most efficient way for water to stay together in a world that is always trying to pull it apart. Take a slow, deep breath now, feeling your chest rise and fall in a steady, comfortable rhythm. As you exhale, imagine the air around you expanding just as the atmosphere stretches out across the horizon. In this vast space, water molecules are constantly testing the limits of their own bonds. Surface tension is what allows a raindrop to maintain its integrity as it eventually falls through the sky, resisting the urge to simply shatter into a fine mist. It is a quiet, persistent strength, a refusal to be separated by the winds or the gravity that tugs at it. Even when water is in its liquid form, it carries this memory of togetherness, a structural bond that keeps the cycle cohesive. But before these droplets can grow large enough to be seen or felt, they exist as part of a much more subtle system within the air itself. The atmosphere is filled with this potential, a hidden moisture that we cannot see with our eyes, but can often feel on our skin on a warm summer evening. This leads us into the world of humidity, the measure of just how much water the air is currently cradling in its invisible arms. As the temperature of the atmosphere shifts, so too does its ability to hold on to this water, creating a delicate balance that dictates the very breath of our planet. This invisible architecture of moisture is the next step in our journey, moving from the physical tension of a drop to the vast hidden weight of the air that surrounds us. The air that surrounds you right now, even in the quietest room or the most parched desert, is never truly empty. It carries a hidden weight, a silent cargo of water vapor that moves with every breeze. We often think of the atmosphere as just a mixture of gases, mostly nitrogen and oxygen. But it is also a vast invisible reservoir. This brings us to a fundamental truth of our world. The air is a container, and its capacity to hold water is always changing, influenced by the warmth of the day and the cool of the night. This capacity is dictated primarily by temperature. Imagine for a moment that warm air is like a vast open ballroom where water molecules can dance freely without bumping into one another. Because the molecules in warm air are moving so quickly and are spread further apart, they provide more room for water vapor to exist as a gas. Cold air, by contrast, is more like a crowded hallway. Its molecules move slowly and stay closer together, meaning they cannot support as much vapor before it begins to cluster back into a liquid state. This is why a basement might feel damp in the summer, or why your breath turns into a soft white mist on a frosty morning. The air simply reaches its limit. When we speak of relative humidity, we are talking about how full that invisible container currently is. If the relative humidity is 50%, the air is holding exactly half of the water vapor it is capable of carrying at its current temperature. It is a delicate, shifting balance, a percentage that fluctuates with every degree the sun provides or the night takes away. When that number reaches 100%, the air is said to be saturated. It has reached its saturation point, the threshold where it can no longer hold its secret cargo in a gaseous state. It is full, content, and ready for a change. There is a beautiful, quiet irony in the way this moisture affects the atmosphere. On a muggy afternoon, we often describe the air as feeling heavy or thick. It seems to cling to us, making our movements feel a bit more deliberate and slow. Yet, in the realm of physics, humid air is actually lighter and less dense than dry air. This seems counterintuitive, doesn't it? We naturally imagine the added water adding weight, but a molecule of water vapor made of 2 tiny hydrogens and 1 oxygen is actually lighter than the molecules of nitrogen and oxygen that make up the bulk of our atmosphere. When water vapor enters a pocket of air, it pushes out those heavier molecules to make room for itself. This means that as the air becomes more moist, it becomes more buoyant. It begins to feel a subtle upward pull from the world above. This invisible architecture of the atmosphere, where warm, moist air is actually lighter than the cool, dry air around it, is what sets the entire sky in motion. It creates a landscape of invisible towers and valleys, where the air we breathe is constantly seeking its level, pushing upward against the weight of the world. As you rest there, perhaps feeling the gentle weight of your own blankets, imagine this invisible lightness beginning to take hold in the world outside. The air isn't just sitting still. It is preparing for a journey. This moist, buoyant air, warmed by the gentle heat of the earth below, is ready to leave the surface behind. It is the beginning of a slow, steady ascent, a rising tide of vapor that will eventually shape the very clouds we see drifting past our windows. This upward movement is the next chapter of the water's story, as it begins to climb toward the quiet, cool heights of the upper atmosphere. Imagine, for a moment, the ground beneath a quiet field or a sleeping forest. Throughout the day, the sun has been pouring its gentle energy down upon the earth. But here's a curious thing. The sun doesn't actually heat the air directly. The atmosphere is mostly transparent to the sun's rays, allowing that warmth to pass right through, much like light passing through a clear window. Instead, the sun warms the dark soil, the ancient stones, and the broad leaves of the trees. It is the earth itself that becomes warm to the touch, and it is the earth that then shares its heat with the very thin layer of air resting right against it. This process, where heat moves from the solid ground into the gas of the atmosphere through direct contact, is called conduction. It is a slow, intimate transfer of energy, happening just inches above the grass. Once that air is warmed by the ground, its molecules begin to move faster, pushing away from one another. This causes the air to become less dense, lighter, and more energetic. It begins to pull away from the surface like a soft balloon released into the vastness of the sky. This beautiful upward dance of warm air is known as convection. You can think of it as the rhythmic breath of the planet, a slow, steady exhalation of warmth and moisture. As these parcels of air begin to rise, they form what scientists call thermal columns. These are invisible pillars of rising air that stretch from the warm ground far up into the blue, creating a hidden landscape of movement. Because the earth is a patchwork of different textures, dark plowed fields, cool green forests, and shimmering lakes, the air doesn't rise evenly everywhere. A dark field of soil absorbs more heat than a grassy meadow, creating a stronger, more vibrant thermal above it. These are the invisible elevators of the sky, If you have ever watched a hawk or an eagle circling effortlessly in the sky without once flapping its wings, you are witnessing the silent power of these thermals. The bird has found one of these rising columns and is simply resting upon it, allowing the Earth's warmth to carry it higher and higher. As you lie still, imagine these millions of invisible parcels of air, each one carrying its precious cargo of water vapor, beginning their long journey upward. They are like giant, soft bubbles of warmth, drifting away from the heat of the day. Every second, billions of these molecules are being lifted by the simple physics of heat and gravity. It is a silent, global migration happening all around us, even in the deepest hours of the night as the Earth slowly releases the warmth it gathered during the day. These invisible elevators are lifting the moisture toward the stars, moving it away from the familiar world of the ground and into the vast open spaces of the atmosphere. It is a transition from the heavy and the solid to the light and the airy. But as this air climbs, it enters a different realm, a place where the rules of the world begin to shift. The air becomes thinner, the pressure begins to ease, and the very structure of the atmosphere starts to change. The journey is only just beginning, and as we follow these rising parcels higher, we find ourselves moving into a space of quiet expansion. As we follow these invisible parcels of air higher, we begin to feel a change in the very fabric of the sky itself. The atmosphere is not a uniform motion of air. It is a delicate, layered structure, and as we rise, the world below begins to feel more distant and quiet. We are currently traveling through the troposphere, the lowest layer of our atmosphere. It is the cradle of almost all the weather we experience, a thin veil of life-sustaining gases that hugs the curves of the Earth. Interestingly, even though the atmosphere reaches hundreds of miles into space, nearly 80% of its total mass is tucked into this first cozy layer. Gravity acts like a gentle magnet, pulling the vast majority of air molecules down toward the surface, keeping them close to the mountains, the forests, and the sea. As our parcel of air climbs higher, it enters a realm where the air becomes noticeably thinner. On the ground, the air is crowded and dense, with billions of molecules constantly bumping into one another. But as we ascend, those molecules find more room to move. There are fewer of them in every cubic inch of space, and the frantic energy of the surface begins to give way to a sense of openness. This thinning of the air is what scientists mean when they talk about a drop in atmospheric pressure. You can imagine the atmosphere as a soft, invisible blanket draped over the planet. When you are standing on the ground, you are at the very bottom of that blanket, feeling the weight of all the air above you pressing down with a steady, comforting force. But as you rise, there is less and less air above you to provide that weight. The pressure eases, and the air molecules within our rising parcel begin to realize they are no longer being squeezed so tightly. This brings a profound sense of lightness and expansion. Imagine a tightly coiled spring slowly beginning to unwind, or a soft piece of silk being unfolded across a wide, dark table. Without the heavy weight of the upper atmosphere pressing down on it, our parcel of air begins to grow. It stretches outward, its molecules drifting further apart from their neighbors. This expansion is a quiet, natural unfolding, a release of tension that happens every time air makes its journey toward the stars. There is a beautiful freedom in this part of the cycle, a moment where the water vapor is no longer tethered to the heat of the earth, but is instead beginning to occupy the vast silence of the mid-skikati. As you settle deeper into your bed, you might imagine yourself as light as one of these rising parcels, shedding the weight of the day and expanding into a state of pure rest. You're moving away from the friction of the world and into a place of quiet, geometric order. However, this act of expansion, this gentle spreading out of molecules, carries with it a hidden consequence. In the physical world, when things expand without being given new energy, they begin to change in a very specific way. As the molecules move further apart and the pressure continues to drop, the energetic warmth they carried from the sun-drenched ground begins to transform. The air is preparing for its next great transition, a quiet, inevitable cooling that comes from the simple act of growing larger in the thinning ski. This invisible expansion of our air parcel brings us to one of the most elegant concepts in atmospheric science, adiabatic cooling. It is a term that sounds complex, but its reality is as simple and as natural as a long, slow exhale. You may have noticed this principle in your daily life without even realizing it. If you have ever used a canister of compressed air to clean a keyboard, or even felt the nozzle of a spray bottle after a long use, you might have noticed the metal feels strangely cold to the touch. This is because when a gas expands rapidly, its temperature drops. In the vast laboratory of our atmosphere, this same process is happening on a grand scale, silently and constantly, as air rises from the earth. As the molecules within our rising parcel move further apart, they are actually doing a form of invisible work. They are pushing against the surrounding atmosphere to make room for their own expansion. Because our parcel is rising so steadily, it doesn't have time to exchange heat with the air around it. It is like a little island of weather isolated in its journey. To find the energy to push outward and grow, the molecules must use their own internal kinetic energy, the very energy we perceive as heat. As they spend this energy to expand, they move a little more slowly, and the temperature of the air parcel begins to fall. It is cooling itself simply by the act of growing larger in the thinning ski. There is a quiet paradox in this journey. It seems as though, as we rise, we should be getting warmer, for we are technically moving closer to the sun, the great golden engine of our solar system. Yet, the higher we climb, the deeper the chill becomes. This is because the atmosphere is not heated directly by the sun's rays passing through it. Instead, it is heated from the bottom up. The Earth's surface absorbs the sunlight and then radiates that warmth back into the air closest to the ground. As we move away from that radiant floor, we are leaving the heater behind. The thin, high air cannot hold on to the sun's energy the way the dense air at the surface can. We are moving into a realm of beautiful, refrigerated silence. Scientists have observed that this cooling happens at a remarkably steady and predictable rate. In dry air, for every 1,000 feet, our parcel of air rises. Its temperature drops by about 5.5 degrees Fahrenheit. This is known as the dry adiabatic lapse rate. It is a rhythmic, mathematical certainty of the ski. If you were to watch a parcel of air rise from a sun-drenched valley to the peak of a high mountain, you could calculate almost exactly how much cooler it would become. It is a gentle, downward slope of temperature that mirrors the upward slope of the land. As you rest here, you might imagine this steady cooling as a soft, blue mist settling over your thoughts. The frantic heat of the day is being left far below, and the air around you is becoming crisp, clear, and calm. But this cooling serves a vital purpose in the water cycle. Every degree that the temperature drops brings the invisible water vapor closer to a change of heart. Cold air is more compact in its ability to hold moisture than warm air is. As our parcel continues to rise and the temperature continues to fall, it is reaching a critical threshold, a point of no return where the vapor can no longer remain a hidden gas. It is preparing for the exact moment of equilibrium, where the thirst of the air is finally quenched and the first shimmer of a cloud begins to take shape in the cold, thin light. Imagine a specific temperature, a quiet threshold known as the dew point. It is the exact moment when the air, having cooled on its journey upward, can no longer hold its water vapor as an invisible gas. You might think of the dew point as a gentle boundary line in the sky, a place where the transparency of the atmosphere begins to soften into something we can finally see. At this precise temperature, the air reaches a state of saturation. In the language of science, we say the relative humidity has reached 100%. This doesn't mean the air is a liquid. It means the air is like a sponge that has been dipped into a stream until it can hold not a single drop more. It is full, heavy, with the potential for change, and perfectly balanced between the world of the seen and the unseen. In this state of saturation, a beautiful phenomenon occurs called dynamic equilibrium. It is a moment of perfect stillness in the molecular world. At this temperature, the rate at which water molecules evaporate into the air is exactly equal to the rate at which they condense back into a liquid. For every molecule that tries to break away and fly free as a gas, another molecule slows down, loses its frantic energy, and settles into the embrace of its neighbors. They are in a gentle tug of war that has finally found its center. As you reflect on this balance, take a slow, deep breath and notice the air in your own room. Perhaps it feels a little cooler against your skin now, or maybe the fabric of your pillow has a refreshing, crisp chill to it. Let that coolness settle over you, just as it settles over the rising vapor in the sky. There is a profound comfort in knowing that the environment around you is finding its own equilibrium, just as you are finding yours in the quiet of the night. It is a fundamental rule of our world that warmer air has a much greater capacity for moisture than cooler air. In the warmth of the sun-drenched valley, the air molecules were dancing quickly, pushing each other apart and creating vast spaces for water vapor to hide. But as the air climbs into the high, refrigerated layers of the atmosphere, those molecules slow their dance. They move closer together, and the spaces where the vapor once lived begin to vanish. The air literally runs out of room to keep its secrets. And in the very moment the vapor begins to turn back into a liquid at the dew point, it performs one last act of grace. It releases a tiny hidden pulse of warmth, the latent heat it has been carrying since it first left the ocean. This release of energy is a soft thank you to the sky, providing a small burst of buoyancy that helps the air parcel continue its journey. The cloud is not just a collection of water. It is a reservoir of stored solar energy being returned to the atmosphere. We are now at the very brink of visibility. The air is cold enough, and it is saturated with moisture. The stage is set for a cloud to be born. However, the water molecule is a shy traveler. Even when the temperature is perfect and the air is full to bursting, the water cannot always transform on its own. It is a curious truth of physics that in a perfectly clean sky, water vapor might not condense, even if the temperature drops well below the dew point. To make the leap from a ghost-like gas to a visible droplet, the water needs a hand to hold. It needs a tiny solid foundation, a microscopic seed around which it can gather and begin its new life in the light. Imagine a sky that is perfectly clear, yet so heavy with moisture that you can feel its weight on your skin. Without a tiny bit of solid matter to cling to, the water vapor in the atmosphere would simply remain a ghost, unable to find its form. It is one of the most surprising secrets of our world that the soft, ethereal clouds we see floating above us are actually built around tiny cores of solid earth. These microscopic anchors are known as cloud condensation nuclei, or CCN for short. You might think of them as the seeds of the sky, the quiet foundations upon which every cloud is constructed. Without these microscopic seeds, the water cycle would come to a silent, shimmering halt. It is a strange fact of physics that in a perfectly clean atmosphere, one completely devoid of any dust or particles, water vapor could reach a state of 400% humidity without ever turning into a liquid. This is a state called supersaturation. In such a world, the air would be thick and heavy with moisture, yet the sky would remain stubbornly, hauntingly clear. The water vapor molecules would bump into one another in the cold air, but they wouldn't have the strength to stick together on their own. They are like a crowd of people looking for a place to sit. They need a bench, a solid surface to act as a foundation, a tiny cradle where they can gather and grow. These nuclei are incredibly small, often measuring only a fraction of a micrometer across. To give you a sense of their scale, they are about 1/100th the size of the cloud droplets they eventually become. They are far too small for the human eye to see, yet they are everywhere. In a single cubic centimeter of air, a space about the size of a small sugar cube, there might be hundreds or even thousands of these invisible particles. They are the scaffolding upon which the atmosphere builds its beauty, drifting on the silent currents of the wind, waiting for the air to cool and the water to find them. When a water molecule finds one of these tiny specks, it finally has a place to rest. Because the particle is solid, it provides a surface that helps the water overcome its own internal tension. Instead of flying apart or evaporating back into a gas, the molecules begin to layer themselves around the seed, building a tiny sphere of liquid. It is a partnership between the solid earth and the vaporous sky. This is the great interconnectedness of our world. The smoke from a distant campfire, the dust from a farmer's field, and the salt from a breaking wave all provide the very invitation the water needs to become a cloud. As you drift deeper into relaxation, consider how even the grandest things begin with something small and humble. A storm that covers an entire continent is made of billions of individual droplets, and every single one of those droplets is holding onto a tiny grain of the world. The sky is not separate from the ground. They are constantly exchanging gifts. The very air you breathe is carrying the materials needed for tomorrow's rain. These seeds are not all the same, however. They come from every corner of the planet, carried by the winds to the highest reaches of the atmosphere. They are the wandering children of the earth, each with its own story, waiting for the right moment to catch a passing molecule of water. Imagine a wave breaking against a rugged coastline far away. As the white foam crashes, tiny bubbles of air are trapped beneath the surface. When those bubbles rise and burst, they launch a fine mist of seawater into the breeze. The sun quickly evaporates the liquid, but it leaves behind a microscopic crystal of sea salt. This tiny grain is so light that it doesn't fall back to the ocean. Instead, it is caught by a rising thermal and begins a journey that may take it thousands of miles across the globe. Salt is one of nature's most effective cloud seeds because it has a natural affinity for water. It practically pulls moisture out of the air, inviting it to settle. But salt is only one traveler in this invisible caravan. High above the vast stretches of the Sahara or the Gobi Desert, powerful winds lift fine mineral dust into the upper atmosphere. This dust forms great invisible rivers in the sky, crossing the Atlantic or the Pacific in a slow, silent procession. A single grain of sand, weathered by the sun for centuries, might eventually find itself suspended over a quiet forest or a sleepy town half a world away. There are other seeds, too, born from the Earth's more dramatic moments. When a volcano exhales, it sends plumes of fine ash high into the stratosphere, where the particles can remain for years, circling the planet like tiny ghosts. Even the smoke from a distant forest fire contributes to this process. The microscopic bits of carbon and soot provide perfect surfaces for water to call home. Even life itself joins the dance. Tiny spores from ferns, grains of pollen from springtime flowers, and even certain hardy bacteria are swept up by the wind, becoming biological anchors for the clouds. These living particles are often the most efficient of all, sometimes helping ice crystals form even when the air isn't quite cold enough for mineral dust to work. It is a beautiful thought to consider as you rest. The sky above you is a library of the Earth's history. A cloud drifting over a bustling city might be built around a speck of ash from a volcanic eruption in Iceland, or a grain of red dust from the Australian outback. The atmosphere doesn't recognize borders or distances. It gathers the essence of the entire planet and weaves it into the soft white fabric of the sky. Everything is connected in this slow, rhythmic exchange. The air you are breathing now may contain a traveler from a continent you have never visited, waiting for its turn to help a cloud grow. Now, with these billions of tiny travelers positioned throughout the cool, moist air, the stage is set for a change of state. The water vapor molecules, which have been dancing solo in their gaseous form, begin to find these anchors. They aren't just bumping into them anymore. They are beginning to stay. One by one, then million by million, the molecules of water start to coat these microscopic seeds in a thin, shimmering layer of liquid. This is the very beginning of a physical transformation, the quiet, microscopic moment where the invisible becomes visible and a single tiny droplet is born. Imagine, if you will, the very moment a single droplet is born. It is a transition so subtle and so small that it escapes our human senses entirely, occurring on a scale that defies the naked eye. As the water vapor molecules find their microscopic seeds, those bits of salt, dust, or ash we spoke of, they begin to huddle together, shifting from a frantic, high-energy gas into a calm, collective liquid. This is the birth of a cloud droplet, a tiny sphere of water that represents the first physical manifestation of a cloud. To understand just how small these newborns are, we have to look at the world of the micrometer. A typical cloud droplet is roughly 20 micrometers in diameter. To put that into perspective, if you were to take a single strand of hair from your head, the droplet would be about 1/5 the width of that hair. It is a speck of moisture so delicate that it seems more like a thought than an object, because they are so incredibly small. These droplets are nearly weightless in the context of the atmosphere. They are so light, in fact, that even the faintest, most gentle breath of rising air, an updraft so soft you wouldn't even feel it on your skin, is enough to keep them suspended. They don't fall. They simply hover, cradled by the very air that brought them into being. It is the sheer number of these tiny droplets that creates the majesty of the clouds we see from our windows. While a single droplet is invisible to us, they never travel alone. In a single cubic meter of a typical white puffy cloud, an area roughly the size of a large armchair, there are often between 100 million and 1 billion of these individual water droplets. It is a staggering population, a vast, silent crowd of liquid jewels all floating in unison. And yet, despite these enormous numbers, a cloud is still mostly made of air. If you were to take all the liquid water in that cubic meter and condense it into a single pool, it would barely fill a small thimble. The cloud is a masterpiece of diffusion, a structure built mostly of empty space and the softest of mists. As you settle deeper into your pillows, consider the journey these droplets must take to become something more. It takes an incredible amount of cooperation for these tiny specks to return to the earth. You would need to gather approximately 1 million of these microscopic cloud droplets and fuse them together just to create a single, modest raindrop. It is a reminder of how much work the atmosphere does behind the scenes, quietly organizing billions upon billions of tiny parts into the weather that sustains our world. This transition from the invisible dance of water vapor to the visible presence of a cloud droplet is the moment the sky begins to hold its breath. When enough of these droplets gather, they begin to scatter the sunlight hitting them, reflecting the full spectrum of colors back to our eyes. This is why the sky, which was once clear and blue, suddenly develops a soft white veil. The invisible has finally become visible. The gas has become a mist. But this change of state is not merely a visual one. It is a profound energetic event. As each molecule of vapor slows down to join a droplet, it must let go of the energy it carried while it was a gas. It releases a tiny hidden spark of warmth back into the air, a secret signature of the transformation taking place high above. This subtle release of energy is the heartbeat of the cloud, a hidden engine of warmth that we are just beginning to uncover. This hidden warmth is what scientists call latent heat, and it is one of the most beautiful, silent exchanges in all of nature. It is an extraordinary concept to consider as you drift it toward sleep. The idea that energy is never truly lost, only borrowed for a time. Every single molecule of water vapor that rose from the sun-drenched surface of the ocean carried a tiny, invisible parcel of energy within it, like a small, flickering ember of sunlight tucked away in its heart. For hours, or even days, that molecule traveled through the winds, holding on to that warmth. But the moment it touches a cooling seed of dust and transforms back into a liquid droplet, it must let that energy go. It releases that stored sunlight back into the atmosphere as a gentle, microscopic gift of heat. This release of energy is not a small thing. In the grand scale of the sky, the amount of latent heat released during condensation is staggering. To understand the scale of this power, consider that the energy released in a single large storm system can be equal to the energy of several nuclear pulses, yet it happens with the quietness of a falling leaf. In the calm of a summer afternoon, this process is much more subtle, but no less profound. As millions of droplets form within a growing cloud, they collectively warm the air around them. This is fact 81 of our journey. The very act of a cloud appearing actually warms the air it inhabits. It is a soft, thermal signature written into the fabric of the sky. This hidden warmth creates a fascinating tension within the atmosphere because the air inside the cloud is being warmed by this release of latent heat. It becomes slightly warmer and less dense than the clear air surrounding it. As you know from the way a fireplace warms a room, warm air loves to climb, and so the cloud begins to act like a gentle, slow-motion hot air balloon. This is the engine of the cloud, a self-sustaining cycle where the formation of droplets creates the heat necessary to lift the cloud even higher. The more it condenses, the more it warms, and the more it warms, the more it rises, pulling even more moist air up from below to join the dance. It is a wonderful thought to hold as you relax, that a cloud is not just a passive object being pushed by the wind, but a living, breathing structure of energy. It is a masterpiece of soft physics, fueled by the very sunlight that hit the ocean's surface thousands of miles away. This upward surge is what gives certain clouds their distinct, majestic personality. They don't simply drift, they grow. They reach upward into the cooler layers of the atmosphere, stacking layer upon layer of white mist into the blue, building towers of vapor that look as solid as marble, but are as light as a breath. This upward growth defines the shape of the clouds we recognize most from our childhood daydreams. When the air is stable and the energy is released in these focused rising columns, we see the birth of the cumulus cloud. The word itself comes from the Latin for heap or pile, and it describes the way these clouds seem to stack themselves toward the stars. They are the classic puffy white clouds of a fair weather afternoon, standing like silent snowy mountains in the middle of a blue sea. As we watch them in our mind's eye, we can begin to see how their cauliflower-like tops are the direct result of that hidden warmth, pushing the mist higher and higher in a slow, rhythmic pulse of growth. There is perhaps no sight more comforting in the natural world than a scattering of cumulus clouds drifting across a deep blue sky on a warm afternoon. These are the clouds of our childhood drawings, the ones that look like cotton wool or soft white islands floating in a vast sapphire sea. This brings us to fact 86 of our journey. The name cumulus is derived from the Latin word for heap or pile. It is a wonderfully simple description for a structure that is essentially a mountain of moisture piled high by the invisible hands of the rising air. When you look at a cumulus cloud, you are seeing a map of the atmosphere's breadth. The characteristic cauliflower or popcorn shape of these clouds is a direct result of the turbulent, rising columns of air we discussed earlier. As the warm air pushes upward, it doesn't move in a single, smooth sheet. Instead, it rises in distinct pulses or bubbles. Fact 87 is that each rounded lobe or puff on the surface of a cumulus cloud represents a single parcel of air that has reached its cooling point and condensed into mist. These lobes are constantly changing, expanding and dissolving in a slow-motion dance of growth and decay, giving the cloud its textured, three-dimensional appearance. These are often referred to as fair weather clouds, which is fact 88. Their presence usually indicates a stable atmosphere where the air is rising gently but isn't yet being forced into the violent heights required for a storm. They are a sign of a balanced day, where the sun's warmth is being recycled into the sky with a rhythmic, predictable grace. Within these white heaps, the water droplets are incredibly small. Fact 89 tells us they are often only about 10 micrometers in diameter. To put that in perspective, you would need to line up nearly 100 of these droplets just to span the head of a pin. They are so light that the slightest upward movement of air is enough to keep them suspended, defying the pull of gravity. The sharp, well-defined edges of a cumulus cloud are also a fascinating piece of science, forming our 90th fact. Unlike the wispy, blurred edges of high-altitude cirrus clouds, cumulus clouds often look like they have been carved out of marble. This happens because of a process called entrainment. As the moist air of the cloud meets the drier air surrounding it, the droplets at the very edge evaporate almost instantly. This creates a crisp boundary where the white mist ends and the clear blue sky begins. It is a boundary of transition, a visible line between two different states of the atmosphere. As you visualize these iconic white structures, let your mind rest on the beautiful contrast they provide. The brilliant reflective white of the cloud against the deep, infinite blue of the sky is one of nature's most calming palettes. It is a scene of immense scale, but also of immense peace. The cloud is a heavy, massive object, yet it looks as light as a thought, drifting effortlessly on the breeze. But as you look closer at these towers of white in your mind's eye, you might notice a curious geometric detail. While the tops of the clouds are rounded, chaotic, and reach toward the sun in uneven heaps, the bottoms of these clouds are often strikingly, perfectly flat. It is as if they're all resting on an invisible glass floor, precisely aligned at the same height across the entire horizon. This flat base is not an accident of the wind. It is a profound marker of the physics of our world, a boundary where the invisible becomes visible. It is the threshold where the air's hidden secrets are finally revealed to the eye. This invisible floor is known to meteorologists as the lifting condensation level, or the LCL, which forms our 91st fact. It is a concept that helps us visualize the atmosphere not just as empty space, but as a series of carefully layered thresholds. Below this line, the water remains in its gaseous state, invisible, transparent, and mixed thoroughly with the air. But as a parcel of air rises from the warm ground, it extends and cools. At the exact moment it crosses the altitude of the LCL, the air becomes saturated. It can no longer hold the water as a vapor, and the transition into liquid droplets begins. This is why the cloud seems to start so abruptly, creating that sharp horizontal base that looks like a solid foundation. Fact 92 explains that the specific height of this invisible floor is determined by the relationship between the temperature and the moisture level of the air at the surface. On a very dry day, the air must rise much higher into the colder regions of the sky before it reaches its saturation point, resulting in clouds that sit high above the earth. On a humid day, the air is already close to its limit, so it only needs to rise a short distance before the clouds begin to form. This is why on some days the clouds feel like a distant ceiling, while on others they seem to hang just above the treetops. The reason why an entire field of clouds often shares the same flat base is captured in fact 92. Because the air rising from a particular landscape, perhaps a wide meadow or quiet forest, usually has a very similar temperature and moisture content. All those separate bubbles of air reach their cooling point at the same altitude. It creates a beautiful synchronized architecture across the sky. You're seeing the physical manifestation of a single, invisible layer of the atmosphere where the conditions are exactly right for water to change its form. As we look at these clouds, fact 94 reminds us that the flat base is essentially a visual map of a specific temperature. In the world of science, this is called an isotherm, a line of equal temperature. Every cloud you see resting on that invisible shelf is touching a layer of air that is exactly the same temperature, regardless of how many miles wide the horizon may be. It is a moment of profound atmospheric harmony. Fact 95 highlights that this level is where the air temperature and the dew point finally meet. It is the point of perfect equilibrium. Above this line, the cloud is free to grow, to billow, and to reach toward the sun in chaotic, beautiful heaps. But below this line, the physics of the air simply will not allow the droplets to exist. They evaporate back into the invisible realm the moment they try to sink. As you reflect on this invisible floor in the sky, take a slow, comforting breath. Imagine yourself standing in a vast open field, looking up at a fleet of white cumulus clouds. Notice the stillness of their bases. They look so stable, so grounded, and as they drift slowly on the breeze, there is a deep hidden order within the chaotic beauty of the sky. Even something as wild and shifting as a cloud follows a precise geometric rule. Let the sight of that flat, soft horizon settle your mind. Everything in the natural world has its place, its threshold, and its time to appear. But while the shape of the cloud is defined by these invisible lines of temperature, its presence is defined by light. As you gaze at these structures in your mind, you might notice the brilliant pure white of their tops, contrasted with the softer, shadowed grays of their flat bases. This play of light is not just beautiful, it is a window into the very nature of how water interacts with the sun's energy. It leads us to wonder why something made of clear water and invisible air can appear so brilliantly, opaquely white against the deep blue of the infinite Skyfax 96. Brings us to the heart of this mystery. The reason clouds appear so vibrantly white. It is a beautiful paradox that clear water droplets and transparent air can combine to create something that looks as solid and bright as a mountain of snow. This happens because of a phenomenon called scattering. Unlike the gas molecules of the atmosphere that scatter shorter, blue wavelengths to give the sky its color, cloud droplets are much larger. They are large enough to catch every single wavelength of light that the sun sends toward us. As we explore Fact 97, we find that because these droplets scatter all the colors of the visible spectrum equally, the reds, the blues, and everything in between, our eyes perceive the combined result as a pure, brilliant white. It is as if the cloud is holding the entire rainbow within its mist. But instead of separating the colors, it blends them back together into a single, radiant glow. It is a perfect, balanced reflection of the sun's true light. This leads us to Fact 98, which suggests that a cloud is essentially a giant, soft, three-dimensional mirror. When sunlight hits the top of a cumulus cloud, it doesn't simply pass through in a straight line. Instead, the light bounces from one tiny droplet to another, reflecting and ricocheting through the interior of the cloud like a pinball. This internal scattering is so efficient that much of the light is sent back out toward the sky or toward your eyes before it can ever reach the bottom. This is why the tops of clouds, those parts closest to the sun, look so luminous, almost as if they are lit from within by a hidden fire. But as you look closer at a drifting cloud in your mind's eye, you might notice that while the top is a brilliant white, the bottom, that flat, stable base we spoke of earlier, is often a soft, muted gray. Fact 99 explains that this isn't because the water at the bottom is any different or dirtier than the water at the top. It is simply a matter of depth and density. As a cloud grows taller and more robust, it becomes harder for the sunlight to find a path all the way through to the bottom. The droplets above have already scattered or reflected most of the light away, leaving the base in a cool, peaceful shadow. The gray you see is simply the absence of light that has been caught higher up in the heap. In fact, 100, we realize that the darker a cloud looks from below, the more impressive its height and volume truly are. A deep charcoal-colored base is a sign of a massive vertical structure above you, a tower of water droplets so thick and numerous that the sun's rays are almost entirely blocked. The cloud in its silent vastness has created its own private twilight beneath it. It is a giant, floating shield of moisture, protecting the earth below from the direct heat of the sun and providing a moment of cool relief to the landscape. When you look up at these clouds, they seem so airy and ethereal, like tufts of wool or wisps of steam that might vanish if you reached out to touch them. They appear to have no weight at all, drifting as easily as a soft breath across a quiet room. They seem to belong to the world of the spirit rather than the world of matter. But this visual lightness is perhaps the greatest illusion of the sky. Beneath that soft white glow and those gentle gray shadows lies a physical reality that is surprisingly heavy, a burden of water that defies our common intuition about things that float. As you lie there, imagine one of those fluffy white cumulus clouds drifting overhead. It looks like a pillow, or perhaps a handful of cotton wool caught in a breeze. It appears to be made of nothing more than light and air, something that would weigh no more than a breath if you could hold it in your hands. But fact 101 tells us that this cloud is far from weightless. In fact, it is a massive, heavy, physical presence. Scientists have calculated that a typical cumulus cloud contains about half a gram of water. For every cubic meter of space it occupies, half a gram seems like almost nothing, roughly the weight of a single small paper clip or a few grains of sugar. In the vast open sky, that tiny amount of water is spread out into millions of microscopic droplets, each one so small it remains suspended in the air. But space is large, and clouds are even larger. Fact 102 brings us to the sheer scale of these floating giants. A standard, medium-sized cumulus cloud, the kind you might see on a quiet sunny afternoon, is often about 1 kilometer long, 1 kilometer wide, and 1 kilometer tall. That is a massive volume of air and water, a cubic kilometer of sky. When you multiply that tiny half gram by the billions of cubic meters inside that cloud, the numbers begin to grow in a way that is truly staggering. According to fact 103, that single fluffy cloud overhead weighs approximately 500,000 kilograms. That is 500 metric tons of water suspended in the air above you, moving as silently as a ghost. To help your mind grasp that weight as you drift toward sleep, consider fact 104. 500 tons is roughly the same weight as 100 large African elephants. Imagine 100 elephants standing together, and then imagine them lifted high into the sky, transformed into a soft white mist that glides silently on the breeze. Or, if you prefer the image of the sea, it is the weight of 2 or 3 of the largest blue whales to ever swim the oceans. All of that mass is gathered into one single cloud, held aloft by nothing more than the invisible hands of the atmosphere. We often think of the sky as being light, but it is actually filled with these massive, heavy objects that dwarf the structures we build on the ground. Fact 105 reminds us of the quiet power and balance of the world around us. We walk beneath these clouds every day, never feeling the crushing weight of the water they carry. We see them as airy and fleeting, yet they are among the heaviest moving objects on our planet. There is a profound sense of wonder in the realization that the sky is not empty, but filled with these massive reservoirs of life-giving water, moving with a grace that hides their true substance. It is a comforting thought that something so heavy can appear so peaceful, and that the world is built on systems that can carry such a burden without effort. You might wonder how something that weighs as much as a fleet of heavy airplanes can simply sit there, refusing to fall to the earth. It seems to defy the very laws of gravity that keep us tucked safely in our beds. But the secret lies not just in the cloud itself, but in the air that surrounds and supports it. This brings us to the invisible support system of the sky, where the gentle mechanics of buoyancy allow these hundreds of tons of water to swim through the heavens as easily as a leaf floats on the surface of a still, dark pond. The air beneath those 500 tons of water is far from empty. It is a vast, invisible cushion that works tirelessly to keep the cloud aloft. This is the hidden architecture of the sky, where the simple laws of physics create a support system stronger than any steel beam. Fact 106 explains the role of updrafts in this process. As the sun warms the Earth's surface, the dark soil of a meadow, the quiet stones of a mountain, or the deep greens of a forest, the air directly above it becomes warm and begins to rise. These columns of rising air, often called thermals, provide a constant, gentle push from below. They act like an invisible hand, lifting the cloud and countering the steady pull of gravity that would otherwise bring those droplets back to the ground. Adding to this support is a surprising truth found in fact 107. Moist air is actually lighter and less dense than dry air. In the world of chemistry, a water molecule is made of 2 hydrogen atoms and 1 oxygen atom, giving it a lower molecular weight than the nitrogens and oxygen molecules that dominate our atmosphere. When water vapor fills a pocket of air, it displaces some of those heavier gases. Because of this, the entire cloud becomes a buoyant bubble in the sky. It is lighter than the clear, dry air surrounding it, allowing it to sit comfortably upon the atmosphere as if it were resting on a soft, invisible mattress. Fact 108 looks closer at the individual droplets themselves. Each one is so tiny that it experiences a high amount of air resistance relative to its weight. This means that their terminal velocity, the speed at which they would fall through still air, is incredibly slow, often just a few centimeters per second. In the time it takes for a droplet to fall even an inch, a soft breeze or a tiny updraft has already pushed it back up several feet. It is a delicate, rhythmic dance where the air almost always wins, cradling the water and refusing to let it go. This leads us to the principle of buoyancy in fact 109. Just as a massive ship can float on the surface of the sea because it is less dense than the water it displaces, a cloud floats because of the density of the atmosphere. The cloud isn't just up there. It is physically supported by the weight of the air below it. Fact 110 brings this all together into a peaceful realization. A cloud is essentially swimming through the atmosphere. It is navigating the invisible currents of the sky, drifting and bobbing with the same effortless grace as a swan on a still blue lake. As you imagine this massive, soft structure swimming miles above you, supported by the very air you breathe, you can feel the stability of the world. Everything is held in place by invisible forces, balanced perfectly to ensure that the heavy becomes light. However, this state of floating is not a permanent one. Even as the cloud swims through the blue, it is a living, changing thing. It is a temporary gathering of molecules that will soon move on to their next form, reminding us that even the most massive things in our world are often just passing through. This brings us to the realization that a cloud is not a solid object, but a fleeting sculpture, existing only for a brief moment in the long history of the sky. It is a beautiful thing to realize that these massive floating giants are not permanent fixtures of the sky. Instead, clouds are temporary sculptures carved by the wind. Fact 111 tells us that the life of a single cumulus cloud, the kind that looks like a fluffy white cotton ball, is remarkably short. On average, a single cloud exists for only about 10 to 45 minutes. Even as you watch one drift across the horizon, it is constantly changing, losing its edges to the dry air and gaining new mist from the rising warmth below. Fact 112 explains this further through a process called entrainment. As a cloud moves, it pulls in the drier air surrounding it. This causes some of the tiny droplets at the edges to evaporate back into invisible vapor. While the cloud looks like a solid moving object, it is actually a site of constant birth and disappearance. It is a transition zone where water is appearing and disappearing at the same time, maintaining a delicate balance for its brief time in the sun. If the air is very dry, the evaporation happens faster than the condensation, and the cloud simply thins out until it vanishes. When we look at the water cycle as a whole, Fact 113 reveals that the average time a water molecule spends in the atmosphere is only about 9 days. From the moment it leaves the ocean as vapor to the moment it falls back as rain, it is a traveler in a hurry. The clouds we see are merely rest stops on a much longer journey. Fact 114 reminds us of the contrast between the ancient nature of water and the youth of the clouds. The water in a cloud might be billions of years old, but the cloud itself was born just moments ago and will be gone before the hour is through. Fact 115 notes that the speed of a cloud's dissolution is almost entirely dependent on the relative humidity of the air around it. On a very clear day, you can sometimes watch a small, stray cloud simply vanish into the blue, leaving no trace behind. It is a quiet, peaceful exit, a return to the invisible state of vapor. As you lie there, feeling the weight of your blankets, perhaps you can take a moment to notice your own thoughts. Like these clouds, thoughts drift into your mind, take a soft shape for a few minutes, and then slowly dissolve. They are temporary sculptures of your own inner sky. Take a slow, deep breath, and as you exhale, imagine any lingering worries thinning out, just like a cloud in the afternoon sun. Just as the sky remains vast and blue even after a cloud vanishes, your mind remains a place of deep, quiet peace, regardless of the thoughts that pass through it. There is a profound comfort in accepting the beauty of the ephemeral, knowing that things do not have to last forever to be meaningful or beautiful. But even as a cloud prepares to fade away, something else can happen within its misty heart. Sometimes, instead of evaporating back into the air, the tiny droplets begin to change. They stop being separate, floating specks, and start to seek one another out. As the conditions within the cloud shift, the droplets grow, becoming heavier and more substantial. They are beginning the process of turning from a mist into something that gravity can finally reach, moving toward a moment where they will no longer be able to float, but will instead begin their long, gentle journey back to the earth. Deep within the heart of a cloud, a quiet transformation begins. This is the moment where the mist starts to find its weight and the invisible becomes tangible. Fact 116 introduces us to a beautiful process with a complex name: collision coalescence. It is essentially the way that tiny water droplets begin to join hands. In the warmer parts of a cloud, these microscopic specks are constantly in motion, drifting on the internal currents of air. As they move, they occasionally bump into one another. Instead of bouncing away, they often merge, two tiny lives becoming one slightly larger one. It is the beginning of a journey toward the earth. You might imagine this as a slow-motion dance occurring in the vast gray-white cathedral of the sky. Fact 117 explains that within every cloud, some droplets are naturally just a little bit larger than others. Perhaps they formed around a slightly bigger grain of salt or dust. Because they are bigger, they are slightly heavier, and as they begin to drift downward through the cloud's mist, they act like tiny collectors. As they fall, they collide with smaller droplets that are floating in their path, absorbing them and growing larger with every inch they travel. It is a process of accumulation, a quiet gathering of resources that happens millions of times every second. There is a hidden force at play here as well, something invisible to the eye, but vital to the process. Fact 118 reveals that these tiny droplets often carry subtle electrical charges. Much like the way a balloon might stick to a wall through static, these charges act like a gentle magnetic pull. When two droplets come close, these electrical forces help them overcome the surface tension that might otherwise keep them apart. They don't just touch, they embrace, snapping together to form a single, more stable drop. This invisible attraction ensures that the cloud isn't just a collection of individuals, but a community in the making, bound together by the laws of physics. It is a slow and steady progress, requiring an immense amount of cooperation. Fact 119 tells us that it takes roughly 1 million cloud droplets to create just a single standard-sized raindrop. When you think of a single drop of rain hitting a window pane or a leaf, you're actually witnessing the union of 1 million tiny parts that have found each other in the vastness of the sky. There is a profound strength found in this union of tiny things. Individually, they were light enough to be tossed about by the slightest breeze, invisible and weightless. But together they gain a new sense of purpose and a shared destiny. Take a moment now to feel the stillness of your own room, the way the air rests quietly around you. Just as those droplets find one another to create something substantial, allow your own sense of calm to gather bit by bit until it fills the space. You are part of a larger rhythm, a quiet world where even the smallest actions lead to significant changes. Finally, we reach fact 120. There comes a point where the droplet grows too large and too heavy for the updrafts of the cloud to support it. The tug of war between the rising air and the pull of the earth is finally over. Gravity, that gentle and constant force that tethers us all to the world, wins the struggle. The droplet, now fully formed and heavy with its millionfold history, begins its descent. It leaves the soft white cradle of the cloud and begins to fall, marking the start of a long rhythmic return to the world below. But even as these droplets begin to fall in the warmosphere, a different, colder magic is often happening just a few thousand feet higher. The descent of a single raindrop marks the beginning of a long-awaited homecoming. As we move into Fact 121, we must look even higher into the sky, to the very tops of the clouds where the air is thin and biting. Even on the warmest summer afternoon, the upper reaches of the atmosphere remain a kingdom of ice. Here, the temperature frequently dips well below the freezing point of 32 degrees Fahrenheit. You might imagine that all the water here is frozen solid, but nature holds a curious secret. Much of the water exists as supercooled liquid droplets that remain fluid even when they are much colder than ice. They are waiting for a signal, a tiny nudge, to change their state once again. This brings us to Fact 122, and a beautiful phenomenon known as the Bergeron process. Named after the Swedish meteorologist Tor Bergeron, it describes a quiet, invisible competition happening inside the cold clouds. In these heights, tiny ice crystals live alongside those supercooled water droplets. It is a delicate balance, a frozen dance, where the two forms of water interact in a way that seems almost like a whispered conversation. The ice crystals are the key to unlocking the cloud's bounty, acting as the primary architects of the rain that eventually reaches our windows. Fact 123 explains the science behind this interaction through a concept called vapor pressure. In the simplest terms, ice crystals have a stronger pull on water vapor than liquid droplets do. Imagine a magnet drawing iron filings toward it. The ice crystal acts like that magnet. It reaches out into the surrounding air and gathers the invisible moisture around it. Because of this difference in pull, the liquid water droplets nearby actually begin to evaporate, turning back into vapor just so they can be drawn toward the ice. It is a selfless transformation, a giving of a oneself to help another grow. In fact, 124, we see the result of this process. As the vapor gathers on the ice crystal, it freezes instantly, causing the crystal to grow larger and more complex. These are the beginnings of snowflakes, intricate hexagonal masterpieces formed in the silence of the upper atmosphere. The ice crystals grow rapidly, becoming heavy and ornate as they consume the moisture from the surrounding liquid droplets. This process is so efficient that it is the primary way clouds in the mid-latitudes produce precipitation. It is a reminder that even in the vastness of the sky, there is a meticulous order to how things grow. The payoff of this cold science is found in Fact 125. Most of the rain that falls upon the earth, even the warm, fat drops of a summer thunderstorm, begins its life as a snowflake. As these heavy crystals begin to fall through the cloud, they eventually leave the freezing layers and enter the warmer air below. As they descend, the delicate arms of the snowflake begin to soften and melt. The ice loses its rigid structure, and collapses back into a liquid form. By the time it reaches your garden or the roof of your house, it has completely transformed into a raindrop. It is a profound realization that the refreshing rain of a July afternoon carries with it the memory of the freezing heights from which it came. Take a slow breath, feeling the air move in and out of your lungs just as the water moves through its mill forms. Your body is resting, supported and still, while high above, this silent transformation continues. The snowflake has become a drop, and its journey is now gathering speed. As it leaves the base of the cloud, it enters the open air, beginning a solitary fall toward the ground. This journey is not a chaotic tumble, but a graceful descent, governed by the laws of physics and the shape of the air itself. We are now following that single drop as it makes its way through the vast space between the clouds and the earth. As our raindrop begins its descent, it doesn't just plummet in a chaotic rush. In fact, 126, we encounter the concept of terminal velocity. As gravity pulls the drop toward the earth, the air beneath it provides a gentle, constant resistance. Eventually, these two forces reach a perfect balance. The drop stops accelerating and settles into a steady, rhythmic pace. It is a moment of equilibrium in the middle of a long fall, a governed speed that ensures the rain arrives as a soft touch rather than a harsh impact. You can imagine the air catching the drop like a soft, invisible hand, guiding it down through the miles of empty space. We often imagine a raindrop as a sharp, pointed teardrop, but Fact 127 tells a different story. In reality, water is a master of efficiency and surface tension. When a drop is very small, less than a millimeter across, surface tension is the dominant force. It pulls the water inward from all sides with such strength that it creates a nearly perfect tiny sphere. These microscopic marbles of water are so light and so round that they drift through the air with almost no effort, catching the light like miniature pearls. At this scale, the drop is a perfect circle, unbothered by the wind. As the drop grows and gathers more volume, something interesting happens in Fact 128. The air rushing up from below begins to push against the bottom of the drop as it falls. Imagine a soft pillow being pressed from one side. The bottom of the raindrop begins to flatten out, while the top remains rounded by surface tension. This creates a shape that scientists often describe as looking like the top half of a hamburger bun. It is wide and curved on top, but flat and stable on the bottom. This bun shape is much more aerodynamic for a falling liquid, allowing the drop to remain stable even as it moves through the shifting currents of the atmosphere. If the drop becomes too large, perhaps by colliding with other drops on its way down, it reaches a fascinating physical limit. In fact, 129. Once a drop grows larger than about 4 or 5 millimeters, the air pressure pushing up against its flat bottom becomes so intense that it begins to indent the center. The drop starts to look like a tiny liquid parachute or a hollow bean. Eventually, the pressure becomes too much, and the air blows right through the middle of the parachute, causing the large drop to shatter into several smaller, more stable droplets. It is a natural safeguard of the sky, ensuring that no single drop ever becomes too heavy or too unwieldy. Finally, in Fact 130, we consider the actual speed of this descent. Despite falling from thousands of feet in the air, a typical raindrop reaches the ground traveling only about 10 to 20 miles per hour. This is the gentle speed of a slow bicycle ride or a light jog. Because the air acts as a constant, invisible brake, the rain never gains enough momentum to be anything other than a soft, nurturing presence. It is the atmosphere's way of protecting the delicate leaves, the soil, and the windows of your home, turning a long fall into a graceful arrival. Take a moment to feel the stillness of your own breath. Contrasting with the long, steady journey of the rain, the drop has survived the freezing heights, the transformation from ice to liquid, and the long tumble through the clouds. It has maintained its shape and its rhythm, and now the journey is nearly complete. The vast open sky is behind it, and the solid, waiting world is just inches away. We are now watching as the drop finally reaches the end of its descent, ready to rejoin the earth and begin the next chapter of its eternal circle. The long descent is over. With a soft, rhythmic tap, the raindrop finally reaches its destination, touching the leaf of a fern or the cool, dark soil of a garden. In fact, 131, we witness the process of infiltration. As the drop lands, it is drawn into the earth by the same gravity that pulled it from the clouds. The soil acts like a vast, gentle sponge, its tiny pores and pathways opening to receive the moisture. This is the earth's way of drinking, a quiet replenishment that happens beneath our feet while we sleep. The water doesn't just vanish. It enters a hidden world of roots and minerals, beginning a journey that is much slower and more deliberate than its fall through the sky. However, not every drop is destined for the deep earth. In fact, 132, if the ground is already saturated or the surface is too hard, the water begins to gather and flow. This is known as surface runoff. You might have seen it in the way a small trickle forms in a driveway or how a mountain stream begins to swell after a rain. This runoff is the architect of our landscape, carving out the paths that will eventually become rivers and lakes. It is a more visible part of the cycle, a silver thread of movement that connects the high peaks to the low valleys, always seeking the path of least resistance as it journeys back toward the larger bodies of water that wait in the distance. For the water that does find its way deep into the soil, a different kind of peace awaits. In fact, 133, as the water moves downward, it eventually reaches the saturated zone, often called an aquifer. This is a layer of rock or gravel where every single crack and crevice is completely filled with water. Above this lies the water table, the invisible boundary between the damp earth and the fully submerged world below. Within these aquifers, the water is cradled by the earth, protected from the sun and the wind. It is a massive, hidden reservoir that stays cool and constant, regardless of the seasons changing above. As the water continues to move within these underground spaces, it undergoes a beautiful transformation, in fact, 134. This is the process of percolation. As the water passes through layers of sand, silt, and rock, the earth acts as a natural filter. Impurities are trapped by the soil, and the water picks up tiny amounts of minerals, calcium, magnesium, and potassium, that give it a unique character. It is a slow, patient cleansing a reminder that the Earth is not just a container for water, but a partner in its purity. The journey through these layers can take days, weeks, or even years, depending on the density of the stone and the path the water chooses to follow. The true scale of this patience is revealed in fact 135. While a river might rush at several miles per hour, groundwater moves with a stillness that is almost impossible to imagine. In some dense rock layers, water may move only a few inches in an entire century. This means that some of the water currently resting deep beneath your feet may have fallen as rain during the time of the ancient empires or even earlier. It is a deep geological memory, a slow-motion migration that carries the moisture of the past toward the future. This water isn't in a hurry. It moves with the rhythm of the planet itself, a steady, unwavering pulse that eventually leads it back toward the lowest points of the earth. We are following this slow, hidden current now as it leaves the soil and the stone behind, gradually finding its way back to the ultimate destination of every drop, the vast and ancient cradle of the world's oceans. As the slow, hidden currents of the earth finally meet the salt and the spray, we find ourselves at the edge of the world's great heart, the ocean. This is the place where the cycle both concludes its long journey and prepares to begin all over again. In fact, 136, the ocean is the ultimate reservoir of our planet, holding roughly 97% of all the water on Earth. It is a vast blue expanse that cradles nearly every drop we have ever discussed, a silent witness to the history of the world. When a molecule of water finally reaches these deep waters, it enters a period of profound rest and belonging. This sense of rest is reflected in fact 137, which concerns what scientists call residence time. While a water molecule might only spend 9 days in the atmosphere or a few weeks in a river, once it enters the ocean, it stays there for an average of over 3,000 years. If a single drop of rain fell into the sea during the height of the Roman Empire, there is a very good chance it is still drifting there today, moving through the deep, dark currents. It is a scale of time that invites us to let go of our own hurried schedules, allowing the mind to settle into the slow, steady pace of the deep sea. Within this vastness, the water is never truly still. As we learn in fact 138, there is a massive looping system of currents known as the global conveyor belt. This underwater river moves water from the warm surface of the tropics down to the freezing depths of the poles and back again. A single circuit of this belt can take 1,000 years to complete. It is a slow-motion dance of density and temperature, shifting billions of tons of water across the globe in a silent, rhythmic pulse that keeps our planet's climate in a delicate, life-sustaining balance. As the water moves, it carries the essence of the land with it, leading us to fact 139. The salinity of the ocean, its saltiness, is a result of billions of years of rainwashing minerals off the rocks and into the sea. When water eventually evaporates from the surface to start the cycle again, it leaves these salts behind. This process ensures that the rain that falls on the hills is always fresh and sweet, while the ocean remains a dense, mineral-rich soup that supports a staggering diversity of life. The ocean acts as a giant filter and a storehouse, holding on to the heavy elements while releasing pure vapor back into the sky. The sheer volume of this water provides a final comforting truth. In fact, 140. The ocean acts as the planet's thermal regulator, absorbing over 90% of the excess heat from the atmosphere. Because water has such a high specific heat, it changes temperature very slowly. This means the ocean stays relatively constant, providing a stable, warm embrace for the world. Even as the seasons turn and the winds howl above, the deep ocean remains a sanctuary of stillness and warmth. Take a moment now to imagine the vast rhythmic pulse of the tides. As you lie there, feel your own breath moving in and out, much like the water rising and falling against a distant shore. The moon pulls gently on the sea, and the sea responds with a slow, predictable heave. There is no rush here. The ocean has all the time in the world. It is the planet's great memory, a liquid archive of every storm, every snowflake, and every mountain stream that has ever existed. This scale of time is almost too large to grasp, yet it connects us to everything that has come before. Every sip of water we take and every cloud we watch drifting by is a piece of a story that is billions of years old. As we rest in the knowledge of this eternal return, we begin to realize that the water we see today is not new. It is ancient, a timeless traveler that has seen the world change in ways we can only imagine. Think for a moment about the glass of water that might be sitting on your nightstand or the very moisture in the air you are breathing right now. It is a quiet, staggering truth that the water on our planet is not being created or destroyed in any significant way. Fact. 141 reminds us that Earth is essentially a closed system. The water we have today is the same water that has been here for billions of years, cycling through the sky, the soil, and the sea in an endless loop of renewal. There is no new water. There is only the water that has always been, changing its shape but never its essence. These molecules are incredibly resilient. While a drop of water might freeze into a sharp crystal or evaporate into an invisible gas, the bond between its two hydrogen atoms and one oxygen atom is remarkably strong. It persists through the ages, surviving the rise and fall of mountain ranges and the shifting of entire continents. This leads us to a thought that is as humbling as it is peaceful. Fact 142. Because the total volume of water remains constant. Every molecule has a history that spans the entire life of the planet. The water you used to wash your faces this morning may have once been part of a vast glacier during the last ice age or a tropical lagoon in a world we would no longer recognize. This means that the water you encounter today has been part of countless other lives before yours. Fact. 143 is a concept that often fills the mind with wonder. There is a high statistical probability that at least one molecule in every glass of water you drink once passed through the body of a dinosaur. 65 million years ago, a triceratops might have lowered its head to a riverbank to drink the same atoms that are now part of your world. The water cycle is the ultimate recycler, weaving the biology of the deep past into the biology of the present moment. It is a liquid thread, that connects every living thing that has ever walked, crawled, or flown across this earth. If we look even closer at the atoms themselves, the story becomes even more profound. Fact. 144 tells us that while the water molecule itself might be billions of years old, its ingredients are older still. The hydrogen in your water was formed in the first few minutes of the universe's birth, and the oxygen was forged inside the intense heat of ancient stars that exploded long before the Earth even existed. When you hold a glass of water, you are holding the history of the cosmos. You are partaking in a celestial journey that began in the darkness of space and found its way to this blue marble, where it continues to flow through you. And sometimes this cycle takes a very long detour deep into the earth itself, far beneath the floor of the ocean. Fact. 145 describes how water can be pulled down into the earth's mantle through the slow movement of tectonic plates. It can remain trapped within the minerals of the molten rock for hundreds of millions of years, isolated from the sun, the wind, and the clouds. Eventually, it is released back into the atmosphere through the steam of a volcanic eruption, re-entering the cycle after an eon of silence. It returns to the surface as vapor, ready to become a cloud and fall as rain once more, as if no time had passed at all. There is a deep sense of belonging in this realization. You are not separate from the earth. You are part of its ancient, flowing rhythm. Every breath and every sip connects you to the dinosaurs, the stars, and the very first rains that fell upon the cooling crust of our world. As you drift closer to sleep, let the weight of this history feel like a warm, heavy blanket. The cycle is vast, it is patient, and it is always moving, carrying the memory of the past into the quiet promise of the future with every falling drop. The water knows its way home just as you are finding your way into the stillness of the night. This journey from the deepest mantle of the earth to the highest reaches of the atmosphere never truly reaches an end. It is a masterpiece of change where nothing is ever truly lost, only transformed. Water may freeze into a glacier for 100,000 years, or it may spend a mere afternoon as a wisp of vapor in a summer sky. But it always remains within the embrace of our planet. It is a closed loop, an eternal rhythm that has been playing since the world was young. Fact. 146 reminds us of a comforting stability. The total volume of water on our planet has remained almost exactly the same for billions of years. While it moves from the salty depths to the frozen poles, shifting its shape and its home, the sum of it all is constant. We live on a world that is fundamentally balanced, a blue marble that keeps its most precious resource close to its heart. This balance is maintained by a global scale of breathtaking precision. Fact. 147 tells us that on a planetary scale, the amount of water that evaporates from the oceans and the land every year is almost perfectly matched by the amount that falls back down as rain and snow. It is a rhythmic exchange that ensures the earth neither dries out nor overflows. Even when one region experiences a drought and another a flood, the global system is always seeking equilibrium, moving moisture across the continents to maintain the breath of life. We are fortunate to live in what scientists call the Goldilocks zone of our solar system. Fact. 148 highlights that the Earth is at the perfect distance from the Sun, not so close that our oceans boil away into the vacuum of space, and not so far that they freeze solid forever. This precise positioning allows the water cycle to pulse between liquid, solid, and gas, creating the dynamic environment that allows us to exist. Even as the atmosphere thins at the very edge of the cosmos, the Earth holds on to its treasure. Fact 149 explains that while a tiny amount of hydrogen can escape from the very top of our atmosphere, the vast majority of our water is held firmly by the planet's gravity. It is a self-contained cradle, a sanctuary that has protected this liquid history through ice ages and volcanic eras alike. The water you see today is the same water that will be here for your children's children, millions of years into the future. And finally, fact 150 brings us back to the most intimate truth of all. You are a living, breathing part of this cycle. Most of your own physical being is made of the very same water we have been tracing through the clouds, the forests, and the seas. You are not just a witness to the water cycle, you are a vessel for it. The rhythm of the falling rain is, in a very real sense, the rhythm of your own life. There is a profound security in knowing that these systems are so enduring and so ancient. The clouds that drift past your window tonight are part of a machinery that has functioned without fail for 4 billion years. It is a system that does not require your effort, your management, or your worry. It simply is. It is a constant, gentle hum in the background of existence, a promise that the morning will bring the dew and the seasons will bring their rains. As you settle deeper into your bed, let the weight of your body sink into the mattress, feeling the quiet gravity of the earth beneath you. Outside, in the darkness, the cycle continues its silent work. Somewhere, a leaf is releasing a single molecule of vapor into the night air. Somewhere else, a snowflake is beginning its long, slow descent toward a silent mountain peak. And here, in the warmth and safety of your room, you are held in the care of a world that knows exactly how to sustain itself. Let your breath become as steady as the tides. Let your mind become as calm as a still lake under a silver moon. The journey of the water molecule is long, but it is never hurried, and it always finds its way home. You too have found your way to this moment of rest. Sleep now, while the water moves silently through the world, weaving the past into the future, waiting to greet you in the soft light of a new day. Good night, and sleep deeply.